Welcome everyone to the 2023 Photonics Spectra Summit Series. Thank you all so much for attending the Optical Metrology Summit. And in this session, you'll hear from Olivia Wheeler, an UltraFast Laser Optics Engineer at Edmund Optics, and Vladimir Pervak, Head of Coating Engineering at UltraFast Innovations. Olivia earned her doctorate in physical chemistry and guides customers through choosing the correct optical components for their ultrafast laser systems. Vladimir earned his doctorate in physics and has written more than 200 technical and scientific publications. They're both joining us today to discuss group delay dispersion. If you have any questions or comments, you can type them right into the Summit chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. Olivia, Vladimir, we appreciate you taking the time to present at the Optical Metrology Summit.
Thank you so much for that introduction, Jake. Welcome everyone to our discussion of group delay dispersion metrology. I'm excited to be here on behalf of Edmund Optics and with my colleague, Dr. Vladimir Pervak of UltraFast Innovations. And today we're going to tell you all about group delay dispersion, what it is, why it's important, and then how to measure it. So starting out with a quick overview of the presentation. First, we're going to walk through some general introductions and define some terms and some concepts, and then we'll discuss white light interferometry in general. And then at that point, Vladimir is going to take over and walk us through how a white light interferometer for measuring GDD looks, as well as some example results, and then talk about the challenges that come with making these measurements. And then finally, we're going to conclude and take any questions you might have. So starting off with introductions and definitions. So really, before we can talk about how we're going to measure group delay dispersion, we'll take a step back to first understand what it is and why it's important. Group delay dispersion, or GDD as we'll often call it, is a really important parameter in the ultrafast laser community because it's going to tell us how a particular material, maybe that's an optical medium or a thin film coating, is going to affect the temporal profile of our ultra short laser pulse. Then we actually need to take one more step back and first walk through some basic definitions associated with ultrafast lasers so that we can really begin to understand why GDD is so important in the first place within this field. So ultrafast lasers are lasers that generate pulses on the order of femtoseconds to picoseconds. So those are pulse durations that are around 10 to the minus 15th or 10 to the minus 12th seconds. And those are incredibly fast. But in order to generate these very, very short pulses, we're going to need a very large spectral bandwidth. And we'll talk more about why that's important in just a second. But essentially, this necessity arises from this fundamental relationship between a pulse's temporal profile and its spectral bandwidth. And ultrafast pulses really carry incredibly high peak powers. And that makes sense when we think about the fact that we're squeezing a ton of average, or we're squeezing some average power into this very, very short blip in time. So then these ultra high peak powers combined with very, very short pulse durations are going to enable a wide variety of important applications, such as biological imaging or microscopy, like I'm showing here. So the ultra high peak powers of ultra short lasers in this context are going to allow a material interest to interact with more than one photon at a time. So that means that we're generating a signal from an overall smaller interaction volume, and that creates a higher resolution image like the one I've shown here. And then in addition, the high peak powers of ultrafast lasers also really make them well suited to ablate different materials in a laser materials processing application space. So the short pulse durations are leading to more precise and more efficient cuts because they're producing less thermal interactions like melting, as you might see with a longer pulse laser. And you can see this effect demonstrated really well here in this SEM image that I've provided. And you can see the cuts and channels that are made by the ultrafast laser are really just so much more precise and clean when compared to those made by the nanosecond laser. And then for these same reasons, ultrafast lasers are going to be really important in the healthcare industry, particularly when we're thinking about some ophthalmic procedures like LASIK. So those minimal thermal effects that I talked about previously that are coming from the ultrafast laser are ultimately going to produce less damage to a patient's surrounding tissues within their eye, So less tissue is affected by the procedure, and ultimately the patient will experience less pain and a shorter healing time. Okay, so now we have a better understanding of what ultrafast lasers are and why they're important, where they're used, we can return to beginning to understand GDD. So I mentioned a few moments ago that the short pulses of ultrafast lasers can only be generated by very, very broad spectral bandwidths. And that's because of spectral bandwidth, because spectral bandwidth and pulse duration are what's known as Fourier pairs. So we can see how this relationship really plays out in the figure that I've shown here at the right. So I've got a 10 picosecond pulse shown in green, and we see that spectrally it's really quite narrow. Maybe it's a couple nanometers wide at best. But then as we start to decrease our pulse duration down to maybe 500 femtoseconds, which I've shown here in blue, the spectral bandwidth is going to start to get wider. And then once we get all the way down to 50 femtosecond pulse durations, we really need a quite large spectral bandwidth, like what I've shown here in red. And if you think about the fact that a refractive index of a given material is going to be dependent on the frequency or the wavelength of light passing through, all the wavelengths that are within this short pulse are going to travel through a medium with slightly different speeds. So as a result, if you pass all of this bandwidth through an optical medium, you'll think that the bandwidth, or rather the frequencies within our pulse are going to start traveling at different speeds, and we're ultimately naturally broadening the temporal profile of our pulse as it passes through. But this is not really an ideal situation, right? Because the more that we're stretching our pulse in time, we're ultimately lowering that ultra high peak power. That's what makes our ultrafast laser so advantageous in the first place. So the ultra high peak power that's ablating our material or producing a multi-photon interaction is becoming less and less, therefore removing the advantage of the ultrafast laser in the first place. So ultimately, we're going to want to prevent this sort of temporal broadening so that we can maintain our very well compressed ultrafast pulse that's coming out of the laser in the first place. So now, finally, to answer the question, what is group delay dispersion? Really, it's going to be how we quantify this effect on our ultrafast pulse duration. So now we can take a little bit of a closer look around what happens to our pulse as a result of GDD. So most media, materials that are going to have what's known as normal dispersion will impart a positive GDD. So that means that the redder wavelengths within our pulse are going to travel faster through that optical medium as compared to the bluer wavelengths of our pulse. So imagine that we start off with this really nice compressed laser pulse, and then we pass it through some sort of an optical medium. And that medium can be anything. It could be a lens, it could be an objective, or even air if we're going over really long distances. And once we go through this optical medium, we see that the redder wavelengths are emerging from that medium ahead of our bluer wavelengths. And then the result of this positive GDD coming from this optical medium is going to be that our pulse becomes temporally broadened. And we already discussed how that can be really detrimental to our laser pulse. So then the question really becomes, how can we prevent or even reverse the effects of this positive GDD? And the answer to that question is that we're going to have to create optics or optical coatings that have an equal and opposite GDD in order to balance out that effect and restore the original temporal profile of our pulse. So that scenario could look something like what I've depicted here. We start out with our ultrafast laser pulse that emerges from our laser really nice and compressed. And then we want to pass it through something that applies a positive GDD. It's going to cause our pulse to stretch in time. And ultimately, we want to restore that original pulse duration. So we do that by using some optics with negative GDD, like this compressive mirror pair that I've shown here. And this is, of course, to recover that once nicely compressed laser pulse. But the trick here is that we need to apply a negative GDD that is equal in magnitude to the positive GDD imparted by our optical medium. So then in order to create and then implement the correct mirrors in this situation, we have to be able to measure the group delay dispersion of the particular coating or element to make sure we're getting it right. How we're going to do that? We're going to do that with white light interferometry. So most of you are probably familiar with white light interferometry in the context of measuring surface roughness using some instrument like a zygo. But if we want to extract the GDD of our optical elements, we're actually going to adjust this setup slightly in order to achieve spectral resolution. So instead of using a camera for our detector, we're going to use a spectrometer in this sort of Michelson interferometer setup in order to extract the applied phase of our optic of interest. So the setup of a Michelson interferometer is going to look something like this. You start with a white light source, again, because we're going to do a spectrally resolved measurement. And then we split that into two arms. One that's going to be our test arm, shown here at the right, and one that will be our reference arm that I have here on the bottom. And in each of these arms, we're going to place a mirror that reflects the light back toward the beam splitter. And then once at the beam splitter, the two arms of our interferometer are going to recombine and then interfere with one another, which when measured with the spectrometer is going to produce a spectrum that looks something like what I've shown here, with a bunch of interference fringes across the spectrum of our light source. So now, if we want to extract phase information, we're going to actually move our reference arm in and out of interference with the test arm. And as we step that reference mirror, we're collecting a full spectrum, a full white light spectrum each step. So the data that we're actually recording is a spectrum that includes the interference of the test and the reference arms at each step, allowing us to extract interferograms for all of the various wavelengths in our spectrum of interest. And then we can extract the phase difference between the two arms. So now imagine that we're testing a mirror that has some non-zero GDD, or this could really be any mirror that isn't perfectly matched to the mirror in the reference arm. What's going to happen is that there's going to be a phase difference between those two arms of the interferometer. And if we want to measure the GDD of something like a chirped mirror, we're seeing a phase difference that arises because there's a wavelength dependent penetration depth into the mirror's coating, like I've shown here in the figure at the right. So this means that as we collect interferograms for all the wavelengths in our spectrum, we can then apply a mathematical algorithm that Vladimir is going to talk to us more about to extract that GDD response from this mirror. And that's going to allow us to make sure that we're able to perfectly recompress our pulse. So you can imagine then that this type of metrology is going to be really critical when you're designing and producing optical elements to use with ultrafast laser systems. And ultimately, if you're not able to measure or quantify the amount of GDD present in your particular element, you'll have no idea how it's going to function with your ultrafast laser or how your pulse is going to be affected. All right, so now I'm going to hand it over to Vladimir, who's going to talk more in depth about the white light interferometer system configuration.
Okay, now we go and we will see how the system look like. That's we have a device. I just with the laser pointer. That's how the device look like. We have just computer, and usually the device has some precision. It's in typical and normal case, it covers a range of plus minus 5 femtosecond square for GDD. It's pretty small device. It just requires 450 to 450 space. We can measure the dispersion at different polarization. And the range where we can measure it covers the range from 250 to 2.5 micrometer. Here it's basically the two interferometer, how Olivia already showed to you. It means we can have a few cases. For example, in one case, we just can place metallic mirrors where both arm is the same, or another configuration where we put our test mirrors. We can choose any angle of incidence what we want to use for our test mirrors. And basically, as Olivia already mentioned in the beginning of the talk, we basically combine the signal from both arm and it go to spectrometer. And in spectrometer, we see basically we see the interference. Now let's go and see what kind of difficulties can come. Basically, what can happen? We have a dispersion mirrors, and we need to measure the dispersion of this. And let's now check the two cases. In one case, we will put the interferometers and metallic mirrors, where basically there will be no group delay dispersion. It means that all frequency will reflect in the same time, and there will be no delay between red, green, and blue color. If we take a dispersion mirrors, for dispersion mirrors, it will be a different case. Different frequency will be reflecting different depth of coating, and basically we will get the delay between different frequencies. As you see on the figure here, we will have a delay between red, green, and blue color. And basically what we measure with this device, we measure a time delay between this frequency. As you see on the graph here, usually this time delay is measured with precision much better than 1 femtosecond, what is just imagine 10 to minus 15 power of minus 15 seconds. And now let's go and watch on the raw data which we have on from spectrometer. On right, you can see the two signals, how they look. It means that this is a signal from one arm. Here's a signal from the second arm, basically reference arm and measured arm. And what we will do, we will change the distance. We basically try to combine both signals together in time and see what happens to the signal. What we see now on the figure, we basically see just intensity from one signal and intensity from another signal. As soon we will get some overlap, we will start see some interference. And when we continue this, the interference will become more pronounced and pronounced. As you see now, when we almost overlap and the distances in both arms, it's almost the same, we see very strong interference. And as you see, our signal is actually not a double, but increased by factor of 4, because we're speaking about intensity. And here we have our interference fringes. When we combine the signals completely, what we can see almost no signal if the mirrors are metallic mirrors, or we can see the 4 times our signal from arm. And when we move our sample, continue to move the sample, we basically will see again the interference fringes, and then at some moments they will just disappear, as shown on the figures here. Now what we see, now on the fly, we see the whole data set, what we measure. Basically we measure the, usually we measure between 6,000 to 12,000 data points, which is basically look like on figure. And now what we will do, we will consider each frequency. Here we have a different wavelengths, and we will just do a cut of this measurement for a certain frequency. When we do this, we might immediately see the problems. Here's how the real data look like, and here we have a lot of data, and what basically we need to define from this position, we need to find the maximum. But as you see from this function, it's very difficult to identify the maximum, especially with precision of 1 femtosecond, when the whole range is of like 1,000 femtoseconds. What we will do, we will zoom on this path here, and basically you see it's very difficult to find a maximum with precision of 1 femtosecond. And what we actually do, we basically need to take a set of data. Basically, our devices allowed us to choose what we want. We can exchange our resolution for the wavelengths on our resolution on time. Basically, by decreasing the resolution in wavelengths, we can increase our precision in time. And here you can, see basically we can by using a special algorithm, we can very precisely define the maximum. And for example, the device can give you precision of 3 nanometers and 1 femtosecond in measuring the GD. Here you can see one example where the short mirrors use and how the measurement look from device. Here you can see that basically we have a short pulse, basically the pulse which it potentially can be short, but you still need to compensate the dispersion of it. And basically we use set of mirrors and then we will correct the phase. Here what you can see is an example of one mirror. This is a complementary pair of mirrors. On top of slide, you can see the reflectance of the mirrors. Here are shown the reflectance, and here you can see the GDD. This is a special mirrors. It's complementary pair. It means it's not a one mirrors, but this is basically a two mirrors. One mirror is shown with red, another mirror shown with blue, and average curve is shown with green. With dot lines, you can see our measurement. And actually, if you apply these mirrors for a pulse compression after hollow core fiber, you can see how short the pulses can be compensated. Here you can see the frog traces, here you can see the spectrum and reconstructed phase, and here basically how the electric field look, and you can see that the pulse duration is close to 3 femtosecond. As I say, here's our ranges. Of course, we have a few challenges here. As soon as we approach the shorter wavelengths, we have not much signal, and it's become more difficult to measure, and the same problematic come from range from 2.4 micrometers. That's why our device is limiting, but we continuously working on improvement of our device and extending our range, and I will show one example just in a minute. And here it's another example, as you can see, where I compare the measurement of theoretical data and the measure obtained from the device. With red dots shown the measured data, and as you can see, they are very nice, in very nice agreement with theoretical conclusion. And conclusion is basically there is a two conclusion: we can produce mirrors very nicely, and the second is the device perform very nice measurement, as you can see on graph here. Another example to measure, this is a high dispersive mirrors, which has minus 10,000 femtosecond square. Here you can see the reflectance of this mirror shown on the right bar, and you can see the GDD here. You can see the blue curve. This is a theoretically calculated GDD curve, and measurement shown with the black triangles. With green color, it's shown just arrow bar corridors, where basically to produce such mirrors with minus 10,000 femtosecond square, we need to have a very great precision for our machine. And basically the green color shown what could happen to a blue curve if our errors during the deposition process will be on level of 0.3 nanometers in layers. And here, as I promised, I will show a future steps. As I said, we're always working on extensions, our range of our device. And here, basically example how we show the mirrors, which is measured in range from 1 micrometer to 3 micrometers. And here you can see the theoretical curve shown with dot line and measured curve shown with solid lines, blue and green. At this moment, I would like to come to the conclusion. I hope our talk was informative, and we have convinced you with Olivia that the measurement, the whitelightinterferometer is a good instrument to make a measurement in range from 250 to 2.5 micrometers. We can measure the GDD in range of plus minus 10,000 femtosecond square. This measurement it doesn't include any artifact, as it could be come from different techniques. As this measurement is very precise and very fast, we can, as there is still possibility to extend the ranges, which where we can perform, and the device is pretty small and just require quite small space on a table. I would like to thank you for attention, and now I give word back to Jakob.
Thank you both for joining us to present on group delay dispersion for ultrafast laser optics. Before we wrap up here, I just want to remind everyone in the audience, if you haven't already, you can type your questions and comments into the Summit chat. And do not worry, if you have not been answered yet, you'll be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the Photonics Spectra Optical Metrology Summit. Thank you all so much for joining us.